All righty, good morning, everyone. So today we're going to start looking at, again, start building circuits. So as we talked about last time, what we're going to do now is start looking at simple circuits. So we're going to start doing circuit analysis. So we talked about batteries, again, what are known as EMFs. So again, an EMF is anything that supplies a constant potential difference to our circuits. So it could be a battery, it could be a generator, it could be all kinds of different things. But we talked specifically about the battery. So the next one we're going to talk about is another type of electrical component that you usually find in circuits, which is what's known as a capacitor. So capacitors are widely used electrical components that have uses in our electrical circuits. So the main purpose of using a capacitor is that capacitors actually store energy for later use. Energy for later use. This is the biggest portion on why we actually use capacitors. So basically, a capacitor will either be fully charged or not charged, which means when it's fully charged, it's storing energy. When it's not charged, it's not storing any energy. Right? So this is kind of the main function, the main reason that you're going to use capacitors. Other functions, so others, are capacitors can act as RAM. So especially in old school computers, your RAM is basically just set up from different array of capacitors. So whichever capacitor is charged and whichever one is not charged corresponds to a 0 or a 1. So when it's not charged, that's a 0. When it's charged, that's a 1. So depending on which one is charged, which one's not, your memory, your computer will basically scan through that memory and then it knows what to do from there. Other things this is used for is also surge protectors. So if any of you have a surge protecting strip, which you probably should have if you have it connected to a computer, basically it's just a power outlet that has surge protection in it. That surge protection is just an array of capacitors. Basically the capacitors block the flow of current, at least an instantaneous flow of current. So if your house got struck by lightning, you would have a huge surge of potential, which means you have a huge surge of current. That huge surge of current gives it too much power, which basically will fry your inner workings of your computer. So it's the point of having a surge protector is to make sure that there's not too much current running through, so there's not too much power which is radiated, so the temperature doesn't increase too much, which basically fries all of your electrical components. So these are kind of the uses of capacitors. But again, the main point of a capacitor inside of an electrical circuit is to store energy. So what is then a capacitor? So a capacitor is, typically, it is going to be two conductors. So here's one conductor and a second conductor, which are separated by some sort of spatial distance d. So this is a conductor. This is also a conductor. So these guys are going to be separated by some spatial distance d, and then what we're going to do is we're going to connect this to a power source. So we're going to connect it to a circuit, so that we're going to put a battery across here, which then allows current to flow through, which then allows charge to be put on. So let's say this battery then has a potential difference of delta V. So what will happen is initially, if I put these capacitor plates in here, which have 0 charge initially on them, what will happen then is a positive charge will move out of the battery. So here's my positive charge, go through my electrical circuit, and then get deposited directly onto the top plate. So now my top plate has a single positive charge. But due to the Coulomb repulsion in the bottom plate, then I'm going to have to push away a positive charge. So another positive charge then will leave the plate here and then go through back into the battery. Okay. Which ultimately means that here in the top plate, I'm going to have a single positive charge, or in the bottom plate, I'm going to be an absence of a positive charge, which means that then it's going to have a negative charge. Your battery then will try to put another charge onto this plate, but now there's a positive charge here, so this positive charge that's up here doesn't want to go onto the plate because now there's a Coulomb repulsion between those two charges, which means the battery now has to do work to then push that charge onto this plate. Simultaneously, once that charge gets pushed onto this plate, that will then cause a Coulomb repulsion on this one, causing this one to move away, which means I'll end up with 2 positive charges here, 2 negative charges here. Then my body will try to push another charge from here onto this plate, which means it has to do much more work because now there's more charge on here, there's more Coulomb repulsion to get a third charge on there, which then forces 3 negative charges on this one, and then eventually it will stop. So what'll happen is eventually the amount of work required to put a charge onto this plate will be more than the amount of work that your battery can do, at which point in time charges will no longer be able to be put onto this plate, which means charges will stop moving through the circuit. So what'll happen is initially this thing is going to have a current. We haven't talked about current yet, but it's going to have a current running through it. But that current will eventually go to 0 as this thing becomes fully charged. So the capacitor then is these conductors, where this one ends up having a positive charge of positive Q. This one has exactly the same amount of charge of negative Q. The energy then, which is stored by the capacitor, which we'll formally talk about later, is then equal to the work that the battery had to do to charge up the capacitors. Right? Because each time I have to put a charge on here, my battery has to do work, which means that the energy which is stored is then equal to the work done by the battery. This is where the energy comes from. So the capacitor then gets energy stored by the work which is done by the battery to force charges onto it. So this then is a capacitor. So again, capacitor is just 2 conductors separated by some spatial distance d. Each one of these is going to have some area, but what will eventually happen is when I connect it to a battery, I have a potential difference across there. That's then going to allow an amount of charge to go onto the capacitor, which is then dictated by the capacitance itself. So it turns out that if I plotted the amount of potential across the battery versus the amount of charge which is stored on the plates, what we actually get in this case is actually a straight line, where the slope of this line is what's known as C, which is equal to the capacitance of the capacitor. So what this says then is that what? The charge which is stored on the capacitor is directly proportional to the potential difference supplied by the battery. So Q then is equal to C times delta V, where C again is this capacitance of the capacitor. This is capacitance. So by definition then, C is equal to the charge per unit volts, right? Or per unit potential. So C then has units of coulombs per volt, which is what's known as a capital F, which is what's known as a farad. So the units of capacitance is what's known as a farad. So it's a coulomb per volt, which is the amount of capacitance that this capacitor has. So, things to know about capacitance. Capacitance. First off, capacitance is independent of charge and potential. So capacitance itself is not a function of charge and potential. So it doesn't matter the amount of charge I put on there, it doesn't matter the amount of potential. Since those two are directly related to each other, the more potential I put on there, the more charge I put on there, but since that's equal to a straight line, then the capacitance itself is independent of the amount of charge or voltage. The capacitance only depends on geometry. So the capacitance of a capacitor actually only depends on the geometry of the capacitor. So if I want to have different capacitances, what I have to do then is change the geometry of the configuration, which then changes the capacitance of my capacitor. For example, if we go back to our picture, what does that mean? So that means if I want to change the capacitance of this particular capacitor, one thing I can change then is the spatial separation between the two. So if I want it to be a particular capacitance, instead of having them this distance, I can move them closer and make it this distance instead. Or these guys are going to have some sort of geometry themselves, like a cross-sectional area or an area to them, so I change the area of these objects as well. So this thing only depends on the geometry. Now, for a general geometry, it turns out that you can't actually analytically determine the capacitance. So for an arbitrary geometry, you can't determine the capacitance analytically. Everyone knows what I mean by analytically? It means mathematically. So basically, you can't come up with a closed form expression for the capacitance. So for most capacitors, the way you have to then measure the capacitance is actually just experimentally measuring. So you have to take the capacitor that you make, apply a potential difference to it, measure the amount of charge, take the charge divided by the potential, do that for a different array of different potentials for different charges, and then there extract the capacitance. So for a general geometry, you need to experimentally determine it. Determine C. So again, if here's my capacitor, so here we'll then connect that to a potential. So again, if I put a particular potential difference across here, I'll then measure the charge on this side, Q, which would then have a negative Q on this side. Here's a different color. And then by, again, simply plotting the charge versus the potential for different arrays, we can then again get the slope, where that slope then is equal to the capacitance of the capacitor. Again, for a particular, any general type of geometry. But of course, there are geometries which will allow us to analytically determine the capacitance. So there are selected geometries. So, however, there are select geometries which we can solve. So, question then is, well, if there are selected geometries that we can solve, what are some of those geometries and how do we actually then determine the capacitance? So let's look at a couple of examples. So the first example we're going to look at is the easiest one, which is what is the capacitance of a parallel plate capacitor? So let's say I have a parallel plate capacitor. So here, each one of these two plates has a cross-sectional area A, so they have the same area. This one, let's say, is the positively charged one, so this has a positive charge Q. This one has a negative charge Q, and these guys are separated by a distance of D. So we want to know then, if this thing is fully charged to the charge of Q and minus Q, or down here, Q and minus Q, what then is the capacitance of this capacitor? So let's do that. So let's say here's my two charges, or my two plates. Go with the picture set. So they'll make this one Q, this one minus Q. These guys are separated by a spatial distance of D, which means that we know our electric field points from the positive plate to the negative plate. This is our electric field. Now, back a couple chapters ago, what we said was that the electric field of a sheet of charge, which is what this is then equal to the charge density divided by twice of epsilon naught, which means that the electric field here is the same as the electric field here, where this one points this way, this one also points in this direction, which means the total field then is simply twice of one of these. So the total field inside of the plates then, so E total, is then equal to the charge density divided by epsilon naught. And this guy points in some direction. What's your favorite direction? Molly, what direction do you want that to be? Yeah, X, Y, Z. X, right. This is the X direction. Good. So this is all going to point in the I hat direction. So good. So we now know is that what? Capacitance by its definition then is equal to the charge divided by the change in potential. So this means then if I want to know what's the capacitance of this capacitor, I need to now determine what is the change of potential across these two plates. That's what I need to know. This is the hard part. Do the integral. Right? So from last chapter, what we know is that the change of potential is equal to minus the integral from A to B of the electric field dotted by the differential length. So here, let's call this point A, let's call this point B. So in this case, our differential length is going to point from this direction. So this is going to be my DL. So here, DL then is going to be equal to what? DX in the minus I hat direction. It's going from the top plate to the bottom plate. So this is the X direction. This would be the negative X direction. Good. So let's plug this in. So this then is going to be equal to minus the integral from, let's call this 0. Let's call this D. So I'm going to integrate from 0 to D of the electric field, which is eta divided by epsilon naught, I hat dotted with minus dx in the I hat direction. So here, I hat dotted with I hat gives me 1. This negative sign then is going to make this guy positive. So, it's always in a bad position for you. So what I finally get then is that delta V then is equal to the integral from 0 to D of eta divided by epsilon naught times dx. The eta divided by epsilon naught is simply a constant, so it's going to be equal to eta divided by epsilon naught times the integral from 0 to D of dx. Well, what's the integral of dx? X, valuing from 0 to D, so this is simply equal to eta times D divided by epsilon naught. Eta, though, by definition, is equal to the total charge divided by the area. So this is now going to be equal to the charge times D divided by epsilon naught times the area. So this is then the potential difference across my plates. So finally, we can then say that the capacitance of our capacitor then, which is equal to the charge divided by the change of potential, is then going to be equal to the charge divided by the charge times the distance divided by epsilon naught times the area, which means the charges are going to cancel. So this thing is going to be equal to epsilon naught times the area divided by the distance. This is my capacitance of a parallel plate capacitor. Now, before we move on, as we mentioned a bit ago, remember we said that the capacitance does not depend on the charge, which here, nothing depends on the charge. It does not depend on the potential, which again, nothing here depends on the potential. The only thing it depends on is the geometry. So here, this only depends on the cross-sectional area and depends on the distance. That's it, with an epsilon. So our capacitance, as we can see from here, only depends on the geometry. So here, this says if I want to make my capacitance go up, I'm going to simply take my two plates and move them closer to each other. As this distance gets smaller, the capacitance goes up. Or I'm going to take that cross-sectional area and make it bigger. That's it. It's okay? Now, one interesting thing about this is, let's say you wanted to make a capacitor with a 1 farad worth of capacitance with a spatial distance between the plates of about 1 millimeter. You can easily do a calculation and determine how big the cross-sectional area of the plates would have to be. And what you find out is that the cross-sectional area would have to be about the size of Boston. So if I wanted to make a capacitor based off a parallel plate capacitor with a 1 farad worth of capacitance separated by a spatial distance of 1 millimeter, the cross-sectional area would have to be the same size as Boston. This is why computers were so huge back in the day. We didn't have the technology to make things as small as we can today, to make things like this, which has capacitors in it. So this is why things had to be so big back in the day. We didn't have the technology to make it smaller. Today, we can make things micro-sized. We have nano-sized things that we can actually make. So, good. Let's do another example. So the next example says that, what is the capacitance then of a coaxial cylinder? So basically here, I have a wire which is wrapped by a cylinder on the outside. So it's a coaxial cylinder where the inner radius is B and the radius of the wire on the inside is A, and this thing has a length of L. So we want to know, what is the capacitance of this scenario? So good. So let's look at that. So basically on the inside, I have a wire. Where this thing has a radius of A. That's my radius here. This thing then is shrouded by a cylinder, a hollow cylinder, where this thing now has a radius of B. So let's say then that the inside is the positive charge. This thing is the negative charge on the outside. So that this thing has a what? On the inside, this is going to have a line charge density of lambda. So in this case, again, what we know is that our electric field is going to point from the inside to the outside. So it's going to be the direction of my electric field. And we know from using Gauss's laws that the electric field then is equal to lambda, the line charge density, divided by 2 pi epsilon naught r times, and that's it. And let's say both of these have a length of L to them. So good. So again, we want to know what's the capacitance. So again, we know the capacitance is equal to the charge divided by the change of potential, which means we have to determine the change of potential. The change of potential then, again, is equal to minus the integral from, in this case, we're going to integrate from B to A. We're going to integrate from the outside to the inside of the electric field dotted by the differential length. Now, remember our electric field, though, for the cylinder points only in the r hat direction. So here we're doing is we're integrating from the negative plate to the positive plate, which means here our DL is going to point from the negative plate to the positive plate. So it's going to be my DL, which means DL then is going to be equal to negative DR. Negative DR in the r hat direction. Basically, I'm going to start off at the top plate, integrate then towards the center. So that DL here, I only care about the radial direction, so it's going to be negative DR in the r hat direction. Good. So let's put everything together. So this is going to be equal to minus integral from B to A of the electric field, which is lambda over 2 pi epsilon naught r in the r hat direction, dotted with negative DR in the r hat direction. Now, r hat dotted with r hat is simply 1, so that negative sign then goes off this negative sign. So this is going to be equal to lambda divided by 2 pi epsilon naught, because that is equal to a constant, integral from B to A of dr divided by r. So this time, one thing I will gripe about towards the exam, even though I'm not done with them, I will be done this afternoon, so we get them back tomorrow, is when you write an integral, and you write an integral sign, and you have no dr, or no dx, or no do anything, that is a meaningless statement. Your math professors will be very mad at you. So if I simply had that without anything else, what the hell does that mean? It means nothing, because you're not telling me what you're integrating over. So you always have to have a differential, which means I'm integrating over that. Something I saw in the exam too many times. So I just want to gripe about that for a second, and now I'm done. So okay, so now I just want to integrate dr divided by r, but what's the integral of dr divided by r? The integral of dr divided by r. Back to our pirates. Go ahead, Mom. Natural log, good. So this is going to be equal to lambda divided by 2 pi epsilon naught times then natural log of r evaluated from B to A. Now again, remember natural log of A minus the natural log of B is the same thing as natural log of A divided by B. So I can finally rewrite this as delta V is equal to lambda divided by 2 pi epsilon naught natural log of A divided by B. Now, remember that lambda, though, is the total charge divided by the total length, which means lambda is the total charge of the interior one divided by its length. So this is also equal to lambda divided by 2 pi epsilon naught L times the natural log of A divided by B. So this is my change of potential going from the outer negative plate to the positive plate. What's up?
Q
Oh, yes. Thank you, Clayton. Sometimes I get excited. It's okay? So good. So finally, we can say that the capacitance, which is equal to the charge divided by the change of potential, is then equal to, so in this case, I'm going to get the charge divided by the charge times the natural log of A divided by B divided by 2 pi epsilon naught times the length. So again, the charge is going to cancel, so it has no charge dependence. So this is simply equal to 2 pi times epsilon naught times the length divided by the natural log of A divided by B. So this is my capacitance for the coaxial cable. Now, again, just to point out, nothing here depends on charge, nothing here depends on potential. The only thing that it depends on is the length of the capacitor, as well as the area and, well, the radius of both the inner and outer. So again, it only depends on geometry. Everything here is only geometry specific. So again, our capacitors, or the capacitance of the capacitor, only depends on the geometry of the capacitor. Doesn't depend on anything else. Now, let's talk about manufacturing. Let's say you wanted to start a company where you were going to make capacitors. We have companies like that, right? We make and sell capacitors because people are going to want to make electrical components, right? They want to make some sort of circuit. So from a manufacturing standpoint, are you going to make every single available capacitor which may or may not be needed by somebody? Would that be a feasible idea to do? Because let's think about it. How many different capacitances could a person possibly need? The answer is infinite. Because one person may need, 0.2 farads worth of capacitance. Next person might need 0.21 farads worth of capacitance. Next person might need 0.221 farads. So there's an infinite number of different capacitors that you would need, which means that if you were going to manufacture capacitors, theoretically, you would have to manufacture an infinite number of different capacitances. How much money is that going to cost you? Give me a hint. Too much. How much money are you going to make back? Not enough, right? Which basically means that you're going to go bankrupt in about 3 days. Put it that way. So what that means is, from practical standpoints, every company that's going to actually take the time to make capacitors are only going to make a handful of different types of capacitors. Just because from a manufacturing standpoint, again, if you happen to make an infinite number of capacitors, you can't do that. So you can only make a few and then sell those. So that brings up the question then, well, if I can only make a certain number of capacitors, and I need to sell those capacitors to somebody who doesn't need the capacitance of those capacitors at which I'm selling, how do we get around that? Well, the answer to that is we can actually change the capacitance of a capacitor by adding capacitors in series and parallel. So the next question then is, how do we change the capacitance by adding existing capacitors in parallel and series? So this is what we want to know. So it turns out that we can create any capacitance for any capacitor that we want to by simply adding capacitors in parallel and series. We'll talk about how this actually works. So what's the difference between parallel and series? So first of all, if I have my battery, here's my battery, delta V. I'm going to connect that to, say, 3 capacitors. So for capacitors, we usually denote them in a series, in a circuit, by 2 parallel lines, which are exactly the same length. Unlike the battery, which is 2 parallel lines where one is longer than the other one. Right? So for the battery, the long one, again, is the positive side. The short one is the negative sign. For capacitors, they are just equal length. So I'm going to put a few of these capacitors together. These are what we call series. series on the inside. So basically what will happen is when I connect this to the battery, the positive charges then will move on to this plate. So this plate will become positively charged, forcing this plate to become negatively charged. The positive charges from here will then move on to this plate, forcing this one to become positively charged. Coulomb repulsion forces this one to become negatively charged. All those positive charges then will build onto this plate. So this one will become positively charged, forcing this one to become negatively charged. So what will happen then is that this one will become positive, this one will become positive, this one will become positive, this one will become negative, this one will become negative, this one will become negative. Now, this one will have a capacitance C1, this one will have a capacitance C2, and let's call this one capacitance C3. So these are what we call series. And why it's called series is because if you think about the charge moving through the wire, the charge has no other place to go except straight through this circuit. So if I have charge coming out of this battery, it only has the choice to go here, through here, through here, through here, and that's it. Your charge has no choice at all. Your charge has no choice, that's what we call series. Now, what turns out to be true in series is that anything which is connected in series has to have exactly the same charge by charge conservation. Since all the charge has to move through here, the charge here has to be the same as the charge here, which has to be the same as the charge here. So anything which is connected in series all has to have the same charge. So this is going to end up with a charge of Q, this is going to end up with a charge of Q, and this is also going to end up with a charge of Q. This is series. So series equals same charge. Let's talk about parallel. So the difference between series and parallel is, let me draw my circuit here, is that now there's going to be a choice. These guys are connected now in parallel. So let's again say this is C1, this is C2, this is C3. Okay? So why is this parallel? Because here the charge now has a choice. So what will happen then is if I have charge coming out of this battery here, either it can go through this portion, back through here, and then close my circuit this way, or my charge can go through the center part, and then close my circuit this way, or it can come out of the battery, go through the bottom loop, and then back to the battery. This point here and here are what are known as junctions or nodes. So those are points where the charge can split off and go into different directions. Okay? So these points here, this point, and this point are what are called as nodes or junctions. Junctions imply the fact that it has a choice. It can go different directions at what it wants to go. Now, the amount of charge which goes through each one will depend on the size of the capacitance. So it turns out then in parallel, where this thing is in parallel, so this is what we call parallel. Turns out in parallel that charges will be different. So in this case, this one's going to have a charge of Q1, this one's going to have a charge of Q2, this one's going to have a charge of Q3, but what is the same is the potential. So the potential across each one of these guys is identically the same. And again, the reason we can see that is because we know now from lab that if we do a closed loop, we have to have the change of potential. If I start at the battery and come back to the battery, it has to be equal to 0. So that means if I start here and I go across the battery, I gain potential. But then I lose potential across the capacitor, and then I come back through, so I have to be equal to 0. Which means that the potential then across C1 has to be the same as the battery. But if I do that for the red loop, what that means then is the potential across C2 has to be the same as that of the battery. If I do it across the yellow or orange loop here, whichever color you want to call that, that means that the potential across C3 has to be the same as that of the battery. So what's true in parallel then is parallel tells me that the potential is the same. So in series, the charge must be the same. In parallel, the potential must be the same, which means that the potential here, delta V1, must be equal to the potential here, delta V2, which must be the same as the potential V3. So delta V1 is equal to delta V2, which is equal to delta V3. So in parallel, the potentials must be the same. In series, the charge must be the same. So the question then is, if I took these three capacitors and I broke them all down to a single capacitor, or if I took all three of these, which were in series, and I broke them all down to a single capacitor, what would then be the capacitance of that capacitor? This is what we call the equivalent capacitance. So basically what we want to do is we want to break this circuit down so that we can replace this one capacitor by a single capacitor, which is what's called CEQ. Where CEQ is what's called the equivalent capacitance of these three capacitors combined together. So what's happening here is all three of these capacitors are acting as a single capacitor, which is CEQ. So here we want to know what is CEQ. For the potential, or the parallel one, again, we want to do the same thing. So again, I want to break this thing down, erase this, so that this thing also acts as a single capacitor. So this is delta V. This is my CEQ. So again, we want to know what is the capacitance of this equivalent capacitor by combining these three capacitors together. How does that change my capacitance? Does the capacitance go up? Does it go down? And then how do we add all these things together? So let's do both of them. Which one do you want to do first? Series or parallel? Richie, which one do you want to do first? Series, great, let's do series. So let's redraw our diagram. So here's this guy. So we have this, this, this. So again, this is delta V. Let's call this C1, C2, C3. So again, our claim is that we can combine all of these down together so that this is made equal to a single capacitance, which is given by this capacitor CEQ. Now, the charge, which then builds up on top of the CEQ, is exactly the same amount of charge which builds up on top of these here. So each one of these charges is exactly the same as the charge which goes on here. But again, what's different is the potential difference across each one of these. So this has a potential difference of delta V1. This has a potential difference of delta V2. This has a potential difference of delta V3. All three of these potential differences are different. But what must be true about the potential difference here plus the potential difference here plus the potential difference here? What must they sum to? They must sum to what? What's providing the potential? The battery. So that means the potential difference of this guy plus the potential difference of this guy plus the potential difference of this guy have to sum to the potential difference of the battery. So what we now know is that what? The potential difference of the battery must be equal to the potential drop across resistor 1, or not resistor, capacitor 1, plus potential drop across capacitor 2, plus potential drop across capacitor 3. This must be the same. Now, what we now know, though, is that capacitance is equal to, let's do it this way, charge is equal to capacitance times the change of potential, which means we can rewrite then the change of potential as being the charge divided by the capacitance. So that means delta V1 here is equal to the charge divided by C1. Delta V2 is equal to the charge divided by C2. Delta V3 then is equal to the charge divided by C3. Now again, our claim is that this picture here is the same as this picture here, which means that we can rewrite this potential in terms of this charge, which is then equal to the charge on that capacitor, which is then the equivalent capacitor. Okay? So again, All we're saying here is that this is the same as this. So the potential here is the same as the potential here, since there's only two things. This has a charge of Q with a capacitance of CEQ. So this delta V here is the same as this one. So this becomes Q divided by CEQ. Okay? Now again, what's true is that the charge here is equal to the charge here, which is equal to the charge here, since they're all in series, which is exactly the same as the charge here, which means all those Q's are the same. So finally, we can simply cancel out all of these charges. So finally, this tells me that what? 1 over the equivalent capacitance is then equal to 1 over C1 plus 1 over C2 plus 1 over C3, or the sum over I of 1 over Ci. So this says that if I have capacitors connected to each other in series, we have to add all the capacitance to each other to create the new capacitance inversely. What does that do to the size of the capacitance? Does that increase it or decrease it?
Decrease.
Good. It's going to be total different. So what happens here is that this decreases the size of the capacitance. The overall size of the capacitance. Good. So what this does is it decreases the size of the capacitance. Why is that true? Well, that's true because if we go back to our capacitance of the parallel plate capacitor, by putting these things in series, what you're effectively doing is increasing the distance between the plates. As you increase the distance between the plates, the capacitance has to go down. This is the overall effect of it. So what this says is if you have a whole bunch of capacitors, but you need a capacitance less than the capacitors at which you want, you simply add them in series. That decreases the overall size of the capacitance. What happens then in parallel? So let's now do parallel. So draw this one here, and it's C1, C2, and then finally C3. And this is my circuit. Now, again, what has to be true here is that what? The potentials are the same. So delta V1 here is the same as delta V2 here, which is the same as delta V3. But since the potentials are the same, but the capacitances are different, that means that all the charges are different. So Q1 here is different than Q2, which is different than Q3. But if I combine all these things down to an equivalent, so this is my CEQ, this is going to have an amount of charge of Q, right? So my question then is, how does the charge here compare to the sum of those three charges? It has to be the same. So what has to be true here is that the charge which goes through C1, the charge which goes on to C2, and the charge which goes on to C3, if I add all three of those charges together, that has to be the same amount of charge which is on the equivalent capacitor. So I can then say Q then must be equal to Q1 plus Q2 plus Q3. But we also know Q is the same thing as what? C1 times delta V plus C2 times delta V plus C3 times delta V. And that must all be equal to C equivalent times delta V. Since they all are connected in parallel, all the potentials are the same, so we can then divide out all the potentials, which means that in this case, CEQ then is equal to C1 plus C2 plus C3, or in general, we simply add them together. So for capacitors connected in parallel, we simply add the capacitance. What happens in this case? Does it go up or down? It makes it go up. So in this case, this then increases the overall capacitance. In this case, you can think of that I'm adding them in parallel. What I'm doing is I'm increasing the cross-sectional area. If I increase the cross-sectional area, the capacitance has to go up. Happening in these cases. Right? So what this says is if I have a handful of capacitors and I need a capacitance greater than any one of those capacitors, well, I simply add them in parallel. By adding them in parallel, I'm going to make the capacitance go up to equal the amount of capacitance that I need. That's it. So I think we got time for like one example, and we'll do some more next time. So let's do an example. Let's see how all this actually works. Now, these problems are very easy. They're just kind of tedious. Okay? And you'll see why they're tedious. So it's a lot of kind of numbing algebra, kind of tedious, but it's okay. So here we have this simple circuit. So here we have these three capacitors. I have C1, C2, and C3, which are connected to each other in various ways. But here I'm told that C1 is equal to C2, which is equal to C3, which we're calling C. So they all have the same capacitance, which is 12 picofarads. Remember, pico is 10 to the minus 12. Okay. So this one, the only thing I want to know is determine the capacitance of a single capacitor that has the same effect as these guys. So basically, the only thing I want to do is combine all these things down together to find the CEQ. That's it. And then we'll make it more annoying in the next example, but we won't make it that far. So, so let's go ahead and redraw this. So again, here is C2, here is C3, connected then to C1, connected then to my battery. Again, what we want to do is combine all these guys together so we have a final capacitor which has one single capacitance. What's up, Dylan? I'm sorry? No, in this case, I only want to know what CEQ is. Yeah. Yeah. In the next problem, I will tell you the potential because we'll want to know what's the charge and potential and everything across each one, which is when really the annoying part comes in. That's where it becomes really tedious, but for now, let's just kind of do it this way. Okay. So first thing I want to do is identify here what's connected in parallel and what's connected in series. And then we want to do it in steps. So first, once I know what's in series and what's in parallel, I want to combine those things together, and I'm going to draw a new diagram every time I do that. And the reason we're going to do that is basically what Dylan was kind of referring to, is since I didn't tell you what the potential was here, but if I asked you another question like what's the charge on each one of these, what's the potential on each one of these, which we're going to do, I need to know how these things were connected together. Because I need to know if they were connected in parallel, the potential is the same. And if they're connected in series, I need to know that because the charge is the same. So the first thing we're going to do is identify what's connected to what in what. So let's identify what's connected to what. So meaning, is anything here connected in parallel? Yes, what's connected in parallel? So remember, parallel, you're looking for a node. Is there a place where charge has the option to go in different routes? C2 and C3. So automatically I know these two guys are connected in parallel. So good, let's connect those in parallel. So here, I'm now going to draw a new diagram where these guys are connected in parallel. So I'm going to call those C23. That's connected now to C1, which is then connected to the battery. Good. How are C23 and C1 connected? Good. Oh, sure. What was that? Well, I can't write two. Well, I could, but we'll get there. Let's do it in steps. And it's actually not going to be too, well, yeah, because it's in parallel. It'll be 2Z, but we're just going to do it in general, and then we'll use our stuff in there. So let's do baby steps for now. Okay, good. So how are C23 and C1 connected to each other? Is there an option for the charge to go anywhere? No, it has one particular way it can go, which means that these two are connected in series. So here, we're going to go ahead and combine these two together to make our final, which is then CEQ. So again, we're going to do this in steps, and you'll see why tomorrow, why I really want to do these things in steps. But Good. So now we can start collapsing these things together. So now to find the capacitance of C23, we know C23 came from two which were in parallel, which we now know to add capacitors in parallel. We simply add them together, which means C23 must be equal to C2 plus C3. But as Dylan said, C2 and C3 are the same, so that's simply equal to 2C. CEQ came from two which were in series. How do I add things which are in series? Well, we add them inversely. So this says then, that's what 1 over CEQ then is equal to 1 over C1 plus 1 over C23. So CEQ then is equal to C1 C23 divided by C1 plus C23. So here we know C1 is simply C. We know C23 is 2C divided by C plus 2C. So this is the same thing as 2C squared divided by 3C, which is the same thing as 2/3 of C. C was 12 picofarads, so this is equal to 8 picofarads. So my equivalent capacitor for this particular arrangement of capacitances is equal to 8 picofarads. 2/3 of 12 is 8. So tomorrow, we'll start off with another example where now we want to start looking at how much charge and how much potential is across each one of these capacitors as well. Let the tedium begin. So life will begin. So, I'll see everybody tomorrow. Have a good night.